Momentum, cut out every box and cut out the border and cut out every box. So, momentum. Let's talk about a definition. First, definition of momentum. Momentum is inertia in motion. Okay, so what's inertia? Newton's first law of motion. What is inertia?
An object that stays at rest.
Okay, an object at rest stays at rest.
An object in motion stays in motion.
Unless.
Unbalanced force.
Very good. So, momentum is specifically when we're talking about inertia. The part when we're talking about in motion. So, what we're saying here, an object in motion stays in motion. We're focusing on that. When we're talking about an object that's in motion, that's staying in motion. Okay? Now, do you remember from inertia when we said an object in motion stays in motion? What do we say about that motion? All right, that motion is a constant velocity. All right, that motion is a constant velocity. Now, this applies when if we have no friction. All right? If we have no friction, give me an example when we have no friction.
Space.
All right. So if you're in outer space, this applies very well if you're in outer space. Outer space. All right? Remember, if you're in outer space and you throw a ball, it keeps going in the same direction with the same speed forever until another force acts on it. Okay? It is kind of crazy. But that happens because there's no friction. All right? This also applies when an object is at equilibrium. Equilibrium, what's that mean?
Equal, like balance forces.
Those two barely fit side by side, so be careful when you glue them in there. Okay? Object is at equilibrium. All the forces are balanced. Okay, so our little picture here, 50 up, 50 down, 30 to the right, 30 to the left. Forces on that are balanced. The net force equals 0. When our net force equals 0, we are at equilibrium. In either of these two situations, the object will have a constant velocity. Okay? If the object has a constant velocity because all the forces are balanced or there's no friction, then we will have momentum. At this time, give yourself a line of space and then write this down nice and big. P equals mv. Spread it out a little bit so we can label it. All right? So we all know what m is. Mass. And we've dealt a lot with v, which is velocity. So, mass times velocity gives us the momentum. All right, that's a lowercase p. Put yourself a little note here. Lowercase. All right? Why is it so important that I emphasize that that's a lowercase p? Because uppercase P is power. Power and momentum, not the same thing. Okay? All right, so emphasize that's lowercase. Units of measure. What are the units of measure? Try not to use too much space here. What are the units of measure for mass?
Kilograms.
Kilograms. What are my units of measure for velocity? Meters per second. Now, momentum is mass times velocity. The units of measure for momentum are kilograms times meters per second. Mass times velocity. Mass times velocity. Okay? So, honestly, the best way to remember this is just looking at the formula. That's how you remember what the units are. All right, so great, wonderful, lovely. Momentum is one of those things that you inherently already know. You've just never had the words to describe it until now. So, now the space that's left on your page, you have the 4 pictures. We're going to glue these down in order on the left side. I want the snail, followed by an elephant, then a train, and last the bullet. Talk about our different objects. What can you tell me is similar between the objects? Not much, right? What's different? Masses and speeds. So, let's do a little bit of comparison. We're going to compare the relative momentum of these different objects. The mass of a snail, very small. So draw a very small little m. What can you tell me about the relative velocity of a snail? Very slow. I couldn't actually quite think of anything that's really slower than a snail that you'd actually measure. Very small mass, very small velocity. A snail has a very small momentum. Okay, so very small m, very small v, very small p. Let's talk about an elephant. Compared to a snail, mass, we got a big mass. All right? Now, an angry elephant can have a very large velocity. But this elephant's not so angry. He's just kind of walking. But the velocity of an elephant that's walking compared to a snail, it's pretty fast. So we're giving him a pretty good size velocity there. So the momentum of an elephant, it's a pretty good momentum. Decent size. Oh, yes. An angry elephant, you have to use a car to get away from. You cannot outrun an angry elephant. It will trample you. All right. Train. What about the mass of a train relative to an elephant? Significantly larger. Okay? Just one train car is like 4 elephants. And think about how many train cars there would be on there. How many cars are on the train? So we've got a very large mass. I actually couldn't think of anything that has a greater mass that has velocity. That actually moves. No, a jet doesn't even get close to the mass.
Carrier ship.
A carrier ship was the only thing, but I wanted something that travels on land. So
The NASA ship.
No. The NASA rocket's actually pretty small compared to the largest planes.
Ferrari.
All right? So, mass. How about the velocity of a train compared to an elephant? Pretty darn fast. A really large velocity. So the momentum, the relative momentum of a train is ridiculously huge compared to a snail or an elephant even. Okay? Now, a bullet. What about the mass of a bullet?
Tiny.
It's small. It's kind of similar to a snail. So draw a little small m.
Small one?
All right? It's got a very small mass.
22.
Okay? But what about the velocity of a bullet? All right? They're pretty darn fast. Is it going to be faster even than a train?
Yeah.
Your fastest train in the world is still about half the speed of a bullet.
How fast is a bullet?
I looked it up once on YouTube. It's like, I want to say, okay, 400 and something meters per second?
The
Can you
bullet,
dodge it?
No.
the bullet hits first before you hear it.
Yes. Oh,
The
yes.
bullet
Much
hits
faster.
first before you hear it.
So you can
Okay.
dodge it?
So, we have a very large velocity on that bullet. Significantly larger than the train. All right? But it has a very small mass. When you multiply something very, very small to something very, very big, you get something in the middle. So, if you actually take a baby elephant that's walking it will have the same momentum as a bullet. I did the math. So draw a P the same size as the elephant. The momentum of a bullet can be similar to that of the momentum of a baby elephant that's walking slowly.
What do we mean? Momentum.
Momentum, mass times velocity.
You know a magician caught a bullet with his mouth?
Ah, nah.
A magician.
No, David Blaine.
Exactly, it's an illusion.
No, but there was a video. It was just there, they had like a rifle.
It's called blanks.
Oh.
And he has a bullet hitting his mouth. Pops it up.
A blank
Not that
using
difficult.
any gun.
Catch a